Welcome, curious minds, to another deep dive. Have you ever paused to consider the very bedrock of our physical
Or,
universe?
the things we take for granted.
Exactly. The fundamental laws, the constants, the invariances, they dictate everything. From, I don't know, how a ball falls to the bending of space-time around a black hole.
hmm We build everything on those pillars.
For centuries, right. Physicists have built models, run experiments, expanded our understanding, all based on these pillars. But what if, and this is a big
Uh,
what if those very foundations, those concepts of invariance that underpin everything from classical mechanics right through to relativity, what if they've been fundamentally misunderstood?
okay.
What if there's a deeper, maybe more absolute truth just hiding in plain sight, a foundational symmetry just waiting for us to, re-examine our deepest assumptions?
That's a pretty profound question to start with.
Well, today we are taking a monumental leap into just such a possibility. We're diving deep into a pretty groundbreaking paper by Philip Adam Lillian. It's from the Unified Coherence Theory Research Series.
And it's titled Hypergravity Invariance, the Absolute Symmetry of Coherence.
Okay, that title alone is something. Hypergravity invariance.
It is. And look, this isn't just some slight adjustment to existing theories. It's an audacious claim. It introduces a really revolutionary concept.
How so?
It aims to redefine the foundational principles of physics.
Mm-hmm.
It does this by positing an ontological invariance, this is the term used, something that underpins all known physical phenomena.
Ontological invariance. So invariance tied to existence itself, not just how things relate.
Precisely. So prepare yourselves for a journey that honestly challenges deeply ingrained assumptions. It offers a radically new way to look at reality. This isn't just refinement. It feels more like a profound reframing of existence itself.
Okay.
Our mission today, then, is to unpack Lillian's core arguments. We want to really understand why this concept, this hypergravity invariance, is being called, and I quote, one of the deepest fractures in the history of physics.
That's a strong statement. It is. So we're going to explore what it means for invariance to be a property of coherence itself, rather than just frames of reference, and how this idea basically recontextualizes everything we thought we knew about space-time, mass, light, even gravity itself. We need to get into the details, really grasp this complex idea.
And it's crucial for you, the listener, to understand right away that this framework doesn't just dismiss existing physics. It doesn't throw it out.
Right, that's important.
It repositions it. Lillian isn't saying Newton or Einstein were wrong, not at all. He's suggesting they were describing phenomena at a particular relational level.
Relational, meaning how things interact, how they look from certain perspectives.
Exactly. His work offers what he calls a meta-relativistic ontology. Think of it like a higher level view.
Okay.
Where current theories in special and general relativity, even quantum field theory, they get re-understood.
Right.
They become relational approximations valid within certain reduction conditions.
Reduction conditions, like specific circumstances or ways of looking.
Sort of. Like they work perfectly well within certain boundaries or assumptions. So we're not throwing out centuries of empirical success. That's key.
Go ahead.
We're aiming to give that genius an even deeper, more fundamental context. We're trying to move from just describing how things relate to each other to understanding the absolute, unchanging source. The source from which those relations and maybe reality itself emerge.
Okay, let's unpack this right from the top. That term, hypergravity invariance, it definitely grabs your attention. We get invariance, something unchanging, a constant.
Right.
But hypergravity, is this like some new super powerful gravity or something else? What exactly is hypergravity invariance?
Yeah, that's a crucial clarification right at the start. The hypergravity invariance, it's not about a stronger version of gravity, not at all.
Okay.
It signifies a principle that is, let's say, prior to or above, or maybe more fundamental than what we currently understand as gravity.
Okay. So hyper as in beyond or overarching.
Exactly. Think of it as the foundational order maker for the whole universe. What we call gravity, as described by Newton or Einstein, is, in Lillian's view, just a specific manifestation. It's a consequence of this deeper hypergravity invariance.
A consequence, got it.
So, the precise definition, hypergravity invariance is a fundamental symmetry of the universal coherence field that remains unbroken under any transformation or variance.
Wow. Okay, say that again, universal coherence field.
Yes, the universal coherence field.
Yeah.
And this symmetry within it stays unbroken, always, no matter what. That statement alone is the central pillar of the entire theory.
That's huge.
It's not just a fancy term. It's a declaration that there's an absolute, unyielding, perfect symmetry at the deepest level of reality. And everything else just flows from that.
Okay.
It holds what Lillian calls ontological priority,
Meaning?
meaning it establishes the absolute structuring principle beneath both classical and relativistic physics. It's not a property of space-time or of matter. It's described as pre-geometric. It exists prior to and independent of any relational description.
Pre-geometric, before geometry itself exists.
That's the idea. Imagine you're looking at a carefully constructed building. Traditional physics might analyze the bricks, the steel beams, the architectural plans, right? Lillian's saying hypergravity invariance is like the fundamental principles of structural integrity and, I don't know, harmonious design.
Yeah.
The things that had to exist before any plans were drawn or a single brick was laid.
The underlying rules before the structure.
Precisely. It's the underlying rule set that allows the universe to be structured in the first place, and it operates on a level deeper than geometry or specific interactions.
So it's not about what stays the same within a system, like inside space-time, but something more fundamental than the system itself. My mind immediately goes to, how do you even begin to measure or model something that exists before dimensions?
Exactly. That's the challenge.
What's the practical implication of space-time being a projection rather than, the ultimate stage? Can you walk us through the key properties that make this hypergravity invariance so different?
Absolutely. And your question about pre-geometric is right at the heart of the challenge and why this idea is so revolutionary.
Okay.
If spacetime is a projection, it implies there could be properties of this underlying coherence field that aren't bound by our familiar 3+1 dimensions.
Right, like we're missing something fundamental.
Think of trying to understand a 3D object by only ever seeing its 2D shadow. You can learn a lot about the shadow, its shape, how it changes, but you'll always miss a dimension. You'll always be limited by the perspective of the shadow. Lillian's work suggests that when we observe space-time, we're essentially studying that 2D shadow.
And its properties.
And what we perceive as its fundamental properties, like curvature, they're actually the ripples or patterns in the original 3D object casting that shadow.
Okay, so space-time curvature isn't fundamental geometry.
It's an effect of something deeper, the practical implication. Well, physics might need entirely new mathematical tools, maybe things like topological or algebraic structures that don't inherently rely on manifold geometry, smooth spaces.
To describe this pre-dimensional reality.
Exactly. It could open doors to understanding things currently inexplicable within our space-time framework. Maybe new perspectives on dark energy or the nature of quantum gravity. Who knows?
Okay, so let's get into those key properties you mentioned.
Right. So one of its most striking aspects is that it's non-relational.
Non-relational. How does that contrast with, say, Einstein's ideas?
Well, it stands in stark contrast to traditional invariance concepts. Think about Newtonian physics invariance. It was about quantities staying constant under certain transformations, like the laws of motion being the same in all inertial frames. Still relational, in a way. Einstein's special relativity then brought in the invariant speed of light, c. But again, that invariance was defined relative to observers and within frames.
Right, how things look to someone.
Exactly. Lillian's hypergravity invariance, though, is described as independent of frames, observers, or velocity compositions. It simply is.
It doesn't depend on how you look at it.
Or where you were looking from, because it precedes those perspectives entirely. It's an absolute quality of existence, not a conditional one.
Okay, that's a big shift. What else? You mentioned pre-dimensional.
Yes, pre-dimensional. This dives right into the idea that it exists prior to the appearance of spacetime.
Which is hard to wrap your head around.
It is. For centuries, physicists have viewed spacetime as this fundamental backdrop, right? A given, something we just work within.
The stage for reality.
Pretty much. But here, spacetime curvature, which is essential to general relativity, describing gravity, it's not seen as a fundamental geometric property. Instead, it's an emergent property of coherence reductions.
Emergent, so it arises from something else.
Exactly. This truly flips the conventional understanding on its head. Spacetime isn't the stage, it's a projection, maybe, from this deeper coherence field.
Like the statue idea you mentioned earlier.
Yeah, like a sculptor's idea of a statue before they even touch the clay. The idea isn't in the clay, it precedes it and guides its form.
Okay.
So when we see space-time curve around a massive object, according to this, that's not the fundamental fabric bending. It's a specific resonance pattern or configuration of this deeper coherence field that gives rise to the appearance of curved spacetime. It's like the universe literally manifesting its geometry from a more primordial, non-spatial blueprint.
So if I'm picturing this right, space-time isn't the fundamental stage. It's more like a play happening on a deeper, more fundamental stage, which is this coherence field.
That's a good way to put it.
That's a radical idea. It seems to challenge our most basic intuitions about reality. And you mentioned it's also generative. How does this deeper invariance actually create the constants we observe, like C?
Right, the generative aspect is what connects this deep sort of abstract coherence to the concrete physics we actually observe and measure. It means it gives rise to apparent constants, such as the invariant c, the speed of light, without assuming them axiomatically.
Without assuming them. That's the key difference.
That's a crucial distinction, yes. In special relativity, the constancy of the speed of light is a postulate, right? An axiom. The entire theory is built upon it. We just accept it as a given. Here, c isn't a given. It's a consequence. It emerges from this underlying coherence, much like the specific frequency of a musical note emerges from the underlying principles of harmony and the instrument playing it.
So C is like a resonance of the universe's coherence.
That's one way to think about it, yes. It's a dynamic outcome of the fundamental field, not some independent, static truth baked in from the start.
Interesting. And the last property, continuous.
Yes, continuous. This clarifies that invariance is never broken. Variance exists only as a relative measurement artifact.
Meaning any change we see isn't real change at the deepest level.
Essentially, yes.
Yeah.
Any variance we detect, any change, any deviation from what we might expect, any apparent instability is merely a symptom of our limited relational measurements. It's not a true break in the underlying symmetry.
So the universe's absolute symmetry, this hypergravity invariance, always holds true.
According to this theory, yes. Our measurements simply aren't always equipped to perceive it directly because they themselves operate within these reduction conditions that Lillian talks about.
Like the bent ruler measuring the sphere.
Exactly like that analogy.
Yeah.
The ruler will show distortions, the measurements will show variance, but the sphere itself remains perfectly symmetrical. The perceived variance is in our tool or our perspective, not in the fundamental object.
So if this hypergravity invariance is the ultimate source, this continuous unbroken symmetry, what exactly is the universal coherence field, the UFT? How does it tie into all this? It sounds like the true canvas upon which reality is painted.
The universal coherence field, or UFT, is precisely that it's framed as the foundational medium, the engine of this entire framework. Lillian's paper explains that all apparent variances, from the very existence of spacetime to the fundamental properties of mass, the behavior of light, they all arise as derivative phenomena from an underlying field of coherent symmetry.
Derivative phenomena, so effects, not causes.
Right. The UFT is essentially the coherence operator that governs dimensional emergence, field interactions, and energy structuring. It's the singular unified field that dictates how everything manifests.
A coherence operator sounds complex.
Think of it with that symphony analogy again. Imagine a grand symphony, but one that's infinitely complex and kind of self-generating.
Okay.
All the individual instruments, the distinct notes, the different melodies, the rhythms, these are like our physical laws and phenomena. Gravity, electromagnetism, quantum mechanics. They all sound distinct. They interact in complex ways. They seem to follow their own rules.
Right. They look separate.
But in this framework, all of them are just manifestations, expressions, reductions perhaps, of one singular underlying harmonic principle. One absolute musical coherence that governs the entire composition.
And that principle is the UFT.
That singular principle is the UFT, yes.
Yeah.
And its inherent unbroken symmetry is hypergravity invariance. It's proposed as the unifying source for everything we perceive in the universe,
Right.
providing the blueprint and the dynamic process for reality itself.
That's a powerful way to visualize it. A universe playing out its own symphony from a single absolute harmonic principle. But okay, this brings us to a critical question. A real historical puzzle, maybe. If this hypergravity invariance is so fundamental, so self-evident once seen, as the paper suggests, why has mainstream physics missed it for so long? How could something so basic be overlooked?
Yeah.
This is where it gets really interesting because it's not just about a new discovery, but about understanding maybe a historical blind spot, a path not taken in how science evolved.
Indeed. And the paper actually meticulously outlines why mainstream physics has failed to identify this deeper ontological invariance. Doesn't just say they missed it.
It gives reasons.
Yes, it attributes it to several historical and methodological constraints. It's not necessarily that physicists were wrong in their observations or their math.
Oh.
It's more that their foundational assumptions and the very way they approach scientific inquiry inherently steered them away from this deeper layer of reality. It's a testament to how deeply ingrained paradigms can sometimes limit our vision,
Definitely. So let's dive into those reasons. The first one listed is that physics evolved from relationalism, not ontology. What does that mean in practice? How did that historical path blind us?
Right, this point goes straight to the historical path physics took. From Newton to Einstein, invariance has always been treated within the context of frames, observers, and coordinates.
Okay, always relative to something.
Pretty much.
Yeah.
Think about Newton's physics. He had absolute time and absolute space, sure, but motion itself was considered relational. An object's velocity was always relative to some other reference point. There wasn't an absolute at rest. Einstein then famously shifted this, introducing the invariant speed of light, c. But even then, space-time geometry would bend and warp to enforce this symmetry within frames.
Still within frames.
Still within frames.
Yeah.
The crucial part Lillian highlights is that at no point was invariance framed as pre-geometric as something existing prior to and independent of any relational conscription.
They never looked before the frame.
Exactly. And this highlights a deep methodological constraint. Physics traditionally studies what can be measured, right? That's its strength.
Of course.
But as Lillian points out, measurement always occurs within frames. You're always measuring one thing relative to another. A ruler against a table, a clock against a pulse. Always relational.
Okay.
This meant that invariance, by its very nature within these observational limits, it got locked into relational mathematics.
Trapped by the method itself.
In a way, yes. The consequence of this, a really significant one according to the paper, is that when Lorentz invariance was mathematically formalized, physics mistook projective stability for foundational symmetry.
Ah, okay. Explain that. Projective stability.
They observed something constant within the projection within a specific frame of reference under specific conditions, and they assumed that was the absolute underlying reality.
The shadow play analogy again?
Exactly. It's like standing in that cave, observing the shadows cast by a fire, meticulously mapping the constant relationships between those shadows, and never considering the actual objects casting them or the fire itself. We were mapping the shadow world, getting really good at it, and mistaking its internal consistency for the ultimate truth.
That makes perfect sense. We measure what we can, and our tools, our very perspectives, are inherently relational. So we built our whole system on observations that inherently limited our view to these shadows.
Yeah, it's the argument.
Which leads us straight to the second reason, a philosophical inheritance, specifically an anti-metaphysics bias. How did that impact the search for ontological invariance? Did it push it out of acceptable science?
Oh, absolutely. This is a powerful historical current. It deeply shaped what was considered legitimate scientific inquiry for a long time.
How so?
Well, physics after the 19th century carried an anti-ontological bias, largely driven by empiricist and positivist programs. Think of figures like Ernst Mach.
Right, Mach's principle.
Exactly. He argued physics should only deal with observable phenomena. Or later, the Copenhagen interpretation of quantum mechanics, which really emphasized that the wave function just describes our knowledge of a system, not necessarily an underlying objective reality until it's observed.
Shut up and calculate.
Kinda, yeah. These movements pushed a worldview where only measurable quantities exist. Anything that couldn't be directly observed or quantified, anything that hinted at a deeper, unmeasurable reality, well, it was treated as unscientific metaphysics.
So it wasn't even considered science anymore.
Pretty much. So ontological assumptions like an absolute field or invariant substrate, which is exactly what hypergravity invariance proposes, were treated as unscientific metaphysics and just fell out of favor. They became unfashionable, even suspect. Lillian argues that Einstein's success with special relativity further entrenched this position. Because it works so well without needing a deeper substrate, invariance became solidified as the constant inside space-time geometry, not an axiomatic coherence property of reality itself.
So the success reinforced the bias against looking deeper.
That's the idea. Because the foundational substrate, this deeper ontological layer, was never even really modeled or considered legitimate. It just disappeared from the scientific conversation. It was deemed outside the purview of science. By excluding ontology, physics cut itself off from the layer where hypergravity invariance lives. It was actively designed out of the pursuit, creating a kind of self-imposed limitation on what questions could even be asked.
So a combination of how we measure and what we philosophically decided was scientific essentially pushed this deeper truth out of view. We decided not to look there.
That's a fair summary of the argument.
And then there's the third reason, historical lock-in. Lorentz invariance, the mathematical framework underpinning special relativity, became almost sacred. If it works so incredibly well, why challenge it, even at a deeper level?
Exactly. And you can't underestimate the power of success in science. Once Lorentz invariance became the mathematical backbone of so much of modern physics.
Like what?
Well, special relativity, SR, general relativity, GR, quantum electrodynamics, QED, and the standard model field theories. Basically, almost everything fundamental. Once it was embedded so deeply, it became, as the paper puts it, untouchable. It was the gold standard.
You can see why.
Absolutely. Because so much empirical success rests on it. Think of the predictive power. GPS systems needing relativistic corrections, particle accelerators designing experiments based on it, nuclear energy, all rely, fundamentally, on principles derived from or consistent with Lorentz invariance.
Right, it works.
It works incredibly well. So questioning it at the wrong level threatens the formalism, the measurements, and, let's be honest, the funding pipelines. There's inertia there.
Understandable inertia.
Definitely. It created a kind of conceptual bottleneck where any challenge to Lorentz invariance tends to be treated as fringe or ether revivalism, concepts that physics had supposedly moved beyond decades ago.
Yeah.
There's a deep-seated resistance to unsettling a framework that has delivered so much.
But Lillian isn't saying Lorentz is wrong, right?
Exactly. And this is crucial for understanding Lillian's framework. It isn't challenging Lorentz's utility. It's repositioning it. It's seeing it as a relational projection downstream of a deeper, unbroken invariant.
Downstream, like an effect of the deeper thing.
Precisely. It's not saying Lorentz invariance is wrong. It's saying it's not the ultimate truth. It's a highly effective, incredibly useful, practical approximation within a certain domain. Like Newtonian mechanics is still incredibly useful for building bridges, even though we know relativity is deeper. Mainstream physics, the paper argues, doesn't even have the language to see this distinction, which helps explain why this deeper insight seemed, quote, invisible from within their paradigm. They simply don't have the established conceptual tools to differentiate between a foundational symmetry and a projective one, because their entire successful framework is built on that projection.
That's a powerful point about the limitations of existing language and paradigms. If you don't have the vocabulary, you literally can't even perceive the distinction. Okay, next up, the measurement and observer problem. This is a classic conundrum, especially in quantum mechanics. How does it relate to missing ontological invariance? It feels like we're always stuck defining things relative to ourselves, the observers.
You've hit on a critical point there. The core issue highlighted here is that to define invariance, you really need an observer-independent reference, something truly absolute to compare against.
Makes sense.
Yet physics, as it's evolved, never truly established one. Think about special relativity again. Invariance is defined relative to observers. The whole idea is that every observer measures the same speed of light, regardless of their own motion. It's defined by the observer's experience.
Okay.
And in quantum mechanics, you have the infamous observer problem, where the observer problem collapses states. Again, defining outcomes relationally, depending on who or what is doing the observing or measuring.
Right. The outcome depends on the measurement.
So, without a framework for an absolute observer, or equivalently, an observer-independent coherence field physics can't ground invariance in anything deeper than frames. Everything just remains relative to something else without a true, absolute anchor. It's like being stuck in a hall of mirrors. You see endless reflections, but you never see the original source object clearly.
Okay, so how does Lillian's framework propose to solve this?
It offers a potentially profound solution. It places hypergravity invariance in the analectic coherence field. That's Lillian's term for the all-encompassing, maybe self-referential nature of the UFT.
Okay, so invariance belongs to the field itself.
Exactly. And then critically, it shows the observer as a symmetry-reducing operator within that invariant background, not the reference itself.
Symmetry-reducing operator, what does that mean?
It means the act of observation, the act of measurement, isn't the fundamental point of reference for invariance. Instead, observation is an action that interacts with and reduces the pristine, unbroken symmetry of the underlying field. It causes the field to manifest in a particular observable way.
So the observer causes a projection but doesn't define the source.
Precisely. This shift turns invariance into a property of the field, not the frame, something modern physics never formalized. It neatly sidesteps the observer paradox by making invariance inherent to the field, not dependent on any specific observation. Our observation doesn't create the invariance. It merely interacts with it, revealing a limited aspect, a specific projection of its perfect symmetry.
That's a truly elegant way to think about it. Reframing the observer's role from a primary reference point to a kind of filter or reducer of symmetry. Okay, and then there's the ongoing massive fragmentation between quantum mechanics and general relativity, the two pillars of modern physics that notoriously refuse to play nicely together. How does that contribute to the oversight of this deeper invariance? Feels like the biggest unsolved puzzle.
It is indeed one of the monumental hurdles, maybe the monumental hurdle for modern physics. And it directly points, Lillian argues, to the absence of this deeper unifying invariance.
Oh, so?
Well, a foundational ontological invariance would necessarily require, as the paper puts it, a single substrate, where spacetime geometry, gauge fields, quantum amplitudes, and information dynamics all arise from one symmetry.
Yeah.
A single source code for everything.
Right, unification.
Exactly. But physics as it stands today simply doesn't have this. Instead, we have these distinct, incredibly successful, but separate frameworks. We have relativity, which gives us geometric spacetime and its built-in Lorentz invariance. Yeah. We have QFT, quantum field theory, describing fundamental particles and forces using Poincare invariance, renormalization techniques, all that stuff.
Okay.
And then we have cosmology, operating with its ACDM metrics, which only have effective invariances that work within their specific, vast scales.
So different rules for different domains.
Essentially, yes. And critically, none of these frameworks recognize a unified field coherence. They operate with their own internal consistencies, they make mind-bogglingly accurate predictions within their respective domains, but they don't share a common, deeper source for their invariances. They don't speak the same fundamental language at the deepest level. Without that, Lillian argues, invariance gets trapped in projections, Lorentz for GR, Poincare for QFT, instead of being elevated to an ontological operator. Each theory develops its own specific form of invariance that works beautifully within its specific domain. But they all miss the singular, universal source from which all such invariances could potentially emerge. It's like having, 3 different incredibly detailed maps for 3 different regions of the same country. Each map is internally consistent, works perfectly for its region.
But there's no master map showing the whole country.
Exactly.
Yeah.
No master map showing how they all connect to the same underlying geography, the same fundamental reality. Without that master map, we can't see the larger, unbroken symmetry of the entire landscape. We only see the regional consistencies.
You've laid out a really compelling case for why this deeper invariance might have been missed. Historical biases, the limits of measurement, philosophical choices, the success of existing theories locking us in, and this fundamental fragmentation of our scientific view. So after navigating all these intellectual barriers, how does this hypergravity invariance suddenly become obvious once you grasp the new framework? You said the paper claims it's self-evident once seen. So what does this all mean? How do we suddenly see what was apparently hidden in plain sight?
Right. It means that once you truly shift your perspective, once you adopt Lillian's ontological lens, the pieces just seem to, click into place. And the necessity of this deeper invariance becomes, as he describes it, self-evident. It's like finally finding the right pair of glasses.
What are the key realizations that make it click?
There are a few key realizations that crystallize it. First, variance requires a stable comparison space. Think about it. If something is changing, if we're observing variance, we inherently need something unchanging, a deeper constant, to compare it against, to even define that change meaningfully. Our current physics often defines change relative to other changing things, which can lead to a kind of infinite regress if you push it far enough.
Okay, you need a baseline.
You need an absolute baseline. Second, Lorentz invariance only operates inside certain reductions. It's not universally true in the absolute deepest sense. It's true within specific reduced conditions, within specific frames, under specific observational setups. It's conditional.
Right.
And third, measurement itself projects relational shadows. Our very act of observing, our interaction with reality, inevitably creates a partial relational view. It doesn't capture the full absolute picture. It's always a perspective.
Okay, variance needs stability, Lorentz is conditional, measurement is a shadow.
Exactly. Once you truly internalize these points, once you accept the premise that our current understanding might be a limited projection, then it becomes arguably self-evident that there must exist an absolute invariant symmetry underpinning all appearances. There has to be something stable and absolute behind it all.
And that's hypergravity invariance.
That invariant is precisely what Lillian has identified as hypergravity invariance, the coherence symmetry of the universal field tensor, UFT. It becomes obvious now because, as the paper suggests, we've shifted frameworks. We're no longer inside relational physics trying to preserve geometry. We're modeling coherence emergence ontologically.
We're looking at the source, not just the effects.
Exactly. We've moved from describing relations within reality to trying to understand the absolute unchanging coherence that generates reality. It's a conceptual Copernican revolution, in a way, moving from an observer-centric or frame-centric view to a field-centric ontology.
That's a powerful and truly transformative perspective. It really is like discovering the source code behind the program we thought was the entirety of reality. Okay, let's move into the implications of this, because if hypergravity invariance redefines the very foundation, it must dramatically reinterpret some of our most cherished concepts. Starting with this idea that all existing variances are now seen as derivative, not fundamental breaks in reality, but effects.
Yes, this is a fundamental paradigm reversal.
Yeah.
It flips our typical scientific starting point right over. All existing models of physics, as the paper states clearly, assume that variance and invariance are properties of velocity, frames, or measurement perspectives.
That's how we've always done it.
That's how we've always done it. We start with these observable quantities.
Oh.
How fast something moves, what frame we're in, what our detector measures, and we build our theories upwards from there. But in the unified coherence framework, this assumption is reversed. Variance is a reduction artifact of deeper coherence structures.
A reduction artifact, meaning
What we perceive as change or as relative differences between things isn't fundamental. It's a consequence, an artifact of the underlying unbroken coherence being reduced or projected into our observable relational reality. It's like seeing those different colors emerge from a prism. The colors are variances, they're different. But they're all reductions projections of a singular invariant white light entering the prism. The variance emerges from the interaction.
Okay, so if experiments show weird variances.
This means that apparent deviations from Lorentz invariance, for example, if an experiment seems to show something breaking it, maybe a tiny variation in C under extreme conditions, these are not evidence of alternative variances, but manifestations of deeper invariance becoming visible.
So it's not that Lorentz is wrong, but then something deeper is showing through.
Precisely. It wouldn't mean Lorentz invariance is wrong, or that there's some other competing kind of invariance we haven't accounted for yet. Instead, it would suggest that in those specific, perhaps extreme conditions, the experiment is subtly tapping into the deeper coherence dynamics. It's making the underlying hypergravity invariance more apparent, or maybe revealing a modulation of the coherence field itself.
So the variance isn't a breakdown.
No. Therefore, any variance detected in an experiment reflects the limitations of the relational layer, not a breakdown of the absolute coherence field. It's actually a clue, potentially, to the deeper structure, not a crack in the current relational one.
So it's not that our experiments are showing us new types of variances, but rather the limits of our current framework for seeing the deeper invariance, which leads nicely into how relativity itself is then reframed, not refuted. A lot of people might initially worry that a theory like this just dismantles Einstein's entire legacy.
Exactly. And that fear is completely understandable given the profound impact and success of Einstein's work. But this framework, as presented, doesn't seek to dismantle it at all.
That's reassuring.
Instead, relativity is preserved as relational approximation valid within certain reduction conditions. It's seen as an incredibly successful and stunningly accurate model for how things behave within a certain set of observable parameters, especially at macroscopic scales and within certain energy regimes where we normally test it.
So it works where it works.
It works incredibly well where it works. However, its invariance, the famous constancy of C, and the principles of spacetime geometry, is now understood as a projection of a more fundamental coherence structure.
The shadow again?
The shadow again, yes. Crucially, this means that relativity describes relational appearances rather than underlying ontological structure. Einstein's equations brilliantly describe the intricate dynamics of the shadows, how they move and interact, but they don't necessarily define the source object casting them.
Like the clock analogy.
Exactly. Imagine you have that beautifully crafted clock. Relativity accurately describes how that clock keeps time, how its hands move, how it might even slow down under certain conditions like high gravity or speed.
Right. Time dilation.
Exactly.
Yeah.
But it doesn't necessarily describe the fundamental absolute principle of time itself as such a thing exists, or the deeper mechanism from which the clock's very operation emerges. This view allows us to acknowledge the immense utility and predictive power of Einstein's work, while simultaneously providing a potentially deeper, more encompassing understanding of why it works so well and perhaps where its limitations might lie in the grander scheme of things. It could even open avenues for future extensions or modifications under extreme conditions.
Okay, that makes sense. It keeps the utility while adding depth. Now, one of the most fascinating reinterpretations has to be the speed of light, c. For so long, it's been the ultimate constant, hasn't it? An absolute axiom that our universe is built upon.
Absolutely. The bedrock of special relativity.
But in this framework, it's considered emergent. That's huge. How does something we consider so foundational suddenly become a consequence? And I guess, how would we even observe that emergence? Could we see C change?
It truly is a radical departure, isn't it? And it's a point Lillian emphasizes quite strongly. The paper states that the speed of light is not a fundamental constant in itself, but a projection of coherence properties within the vacuum.
A projection of the vacuum's properties.
Yes, this means C isn't just some arbitrary fixed number plucked out of nowhere. It's more like a resonant frequency, perhaps? Or a specific propagation speed that arises naturally from the specific coherent state of the universal coherence field in our local region of the universe.
So its value depends on the field state.
That's the implication.
Yeah.
Its invariance is not axiomatically assumed, but emerges from the coherent vacuum properties defined by the universal field tensor. So again, C isn't a given, it's a consequence, a manifestation of the field's fundamental symmetry and state.
Okay, so how could we observe that? Could it vary?
Well, this is where it gets really interesting, theoretically. Lillian posits that when coherence modulation occurs, light speed deviations may appear relative to the observer, but the underlying invariance, the hypergravity symmetry, remains unaltered.
Coherence modulation, changing the state of the vacuum field.
Something like that. Imagine the vacuum, the empty space around us, isn't truly empty, but is this vibrant, coherent field. If this field's coherence can be subtly modulated or changed maybe by extreme energy densities, perhaps near exotic matter like a black hole singularity, or even through specific quantum field interactions we don't fully understand yet, then the emergent speed of light could, in principle, vary relative to a local observer in that modulated region.
Wow.
Now, we're likely talking about incredibly subtle effects, maybe at energy scales far beyond current experimental reach, or in environments we just can't access or create yet.
So we might not see it easily.
Probably not. But if such observations were made, they wouldn't mean the universe's fundamental rules are breaking down. Instead, it would indicate that we are observing a new, deeper layer of the UFT's dynamic coherence in action. We'd be seeing free behaving as a derivative constant, responding to the underlying field conditions.
While the real constant...
While the hypergravity invariance itself remains perfectly constant and unbroken underneath it all, it's a bit like the speed of sound, varying in different mediums, air, water, steel.
Right. The speed changes, but sound waves still follow rules.
Exactly. The underlying principles of wave propagation remain, but the observed speed changes with the medium's properties. Here, the medium is the very fabric of coherence itself.
So even if we observed light speed varying in some incredibly exotic conditions, it wouldn't mean the universe is broken, but that we're seeing a new layer of its coherence in action, its true underlying nature becoming more apparent.
That's the interpretation offered by this framework, yes.
Okay. This brings us to gravity. Another cornerstone, one of the four fundamental forces, a concept Einstein brilliantly reimagined as geometry. How is gravity reinterpreted here? Not as a force or curvature, but as a coherent structuring principle. This sounds like a complete rehaul.
It is a radical reinterpretation, absolutely.
Yeah.
It fundamentally shifts our understanding away from geometry and towards pure coherence. The paper states, gravity is reinterpreted as a manifestation of coherent selection rather than a force or curvature.
Coherent selection. What does that mean?
For centuries, we've understood gravity either as an attractive force between masses, Newton, or as the curvature of spacetime itself caused by mass and energy, Einstein. Here it's suggested to be neither of those, fundamentally.
Okay, so what is it?
Instead, apparent gravitational effects arise from hypergravity coupling between the coherence field and localized matter-energy distributions.
Hypergravity coupling.
Yeah, imagine the universal coherence field as this vast, interconnected, perfectly symmetrical web of energy and information. When matter and energy exist within this field, they don't just passively sit there or curve space around them, the traditional sense. They actively interact with and, in a way, select specific coherence patterns within this field.
Select patterns.
Yes, these localized matter-energy distributions act as modulators of the UFT. They cause specific hypergravity couplings interactions governed by the deeper hypergravity invariance, and it's these couplings that we then perceive as gravitational effects, the pulling of masses, the bending of light near a star.
So the force of gravity is the emergent effect of this coherence interaction.
That's the idea. It's the consequence of this underlying coherence interaction between the field and matter energy.
And space-time curvature, what happens to that?
Well, space-time curvature is not a fundamental geometric property, but a resonance pattern within the coherence tensor.
A resonance pattern, like ripples.
Kind of. So what Einstein brilliantly described as the geometric warping of space-time is actually, in this view, more like a vibrational or resonance pattern, a specific configuration within the underlying coherence field, shaped by these hypergravity couplings.
In the equivalence principle, gravity equals acceleration.
Even the equivalence principle, that cornerstone of general relativity, equating gravitational inertial mass, becomes a derived consequence of hypergravity invariance.
Derived. So it also emerges.
It also emerges naturally from the deeper symmetry. This means that gravitational invariance itself, the consistent way gravity behaves everywhere, is subsumed within the broader coherent symmetry. It's not a separate phenomenon requiring its own geometric explanation. It's just a specific, localized expression of the universal coherence. It offers a way to explain gravity's fundamental role without making space-time geometry the ultimate arbiter.
This is truly an all-encompassing framework, then. It seems to be trying to connect fundamental constant space-time itself and gravity all back to a single underlying principle of coherence, which sounds like it offers a potential solution to the holy grail of physics unification, bringing quantum mechanics and general relativity together, maybe resolving some of those long-standing paradoxes. How does it specifically address this monumental challenge? Which paradoxes maybe could it help us finally resolve?
Yes, this is where the framework really shows its potential ambition, offering what it claims is a profound pathway to unification. Lillian argues directly that by grounding both quantum and relativity in hypergravity invariance, this approach offers a natural pathway for unifying quantum fields, relativistic spacetime, and cosmological structure.
That's the dream.
It is. The fragmentation we discussed earlier, where physics lacks that single substrate, that single language to explain phenomena across all scales, is directly addressed by proposing the UFT and hypergravity invariance as that missing common foundation.
Yeah.
It provides that shared source code, potentially, from which all these seemingly disparate domains of the quantum world, the relativistic cosmos, can emerge as coherent aspects of a single unified reality.
So, specific paradoxes, like quantum gravity.
Exactly. Consider the problem of quantum gravity.
Yeah.
A huge challenge of reconciling gravity, described by GR as smooth space-time curvature, with quantum mechanics, which describes discrete, probabilistic events at small scales.
We just don't fit.
They don't fit in our current models. But if space-time curvature is just a resonance pattern in the coherence field, and if quantum amplitudes are also expressions of this very same field's coherence, then the entire problem shifts, doesn't it?
How so?
You're no longer trying to quantize geometry itself, which has proven incredibly difficult. Instead, you're looking for the underlying coherent principles from which both the appearance of geometry and the reality of quantum discreteness emerge. The UFT could offer a single language to describe both sides of that coin.
Okay, what about the measurement problem? The observer collapsing the wave function.
Right, the measurement problem in quantum mechanics. That perplexing question of how an observer, or a measurement, seemingly collapses a wave function from a superposition of many possibilities into a single definite state.
It's always seemed weirdly subjective.
It has, but if the observer is framed as a symmetry-reducing operator acting within the invariant coherence field, as Lillian suggests, then measurement isn't magically creating reality out of nowhere. It's causing a specific localized reduction or projection of the field's infinite potential, manifesting one particular outcome consistent with the field's rules.
So it recontextualizes the observer's role.
Yes, potentially without invoking spooky action or complex metaphysical leaps about consciousness creating reality.
Yeah.
It becomes a physical interaction with the coherence field.
And cosmological puzzles, like dark energy.
Potentially, yes. Even broader cosmological puzzles like dark energy, that mysterious force apparently accelerating the expansion of the universe, could find a more natural home here. If the vacuum itself is this dynamic, coherent field with inherent structuring principles and energy, then the energy of this field, its baseline coherent state, might be directly responsible for these large-scale effects. It could act as a kind of background tension or pressure-driving expansion arising naturally from the UFT itself rather than being an ad hoc addition.
Interesting.
And finally, just reinforcing that idea that constants as emergent phenomena is key. The invariance of En, Planck's constant, other fundamental numbers. It means their constancy isn't something we just have to accept axiomatically as brute facts.
Right.
Instead, their constancy emerges from the coherent vacuum properties defined by the universal field tensor. This offers a deeper explanation for why these constants appear constant, linking them directly back to the absolute symmetry of coherence rather than treating them as arbitrary starting points dropped into the universe. This unified perspective, if correct, could finally bridge that conceptual chasm that has separated the physics of the very small from the physics of the very large for so long, providing a singular, comprehensive theory of everything.
Wow. What a journey we've taken today, really diving into the very fabric of reality and challenging centuries of assumptions. Lillian's paper presents a truly profound shift in perspective. So to recap, what we've explored today argues that physics has basically, in his words, mistaken the shadows of invariance for its source. That's quite an intellectual earthquake, isn't it?
It absolutely is. If this framework holds water, it's fundamental. Hypergravity invariance represents the unbroken coherence symmetry from which space-time itself and everything in it emerges.
Yeah.
It offers a radical reframing of the ontology of invariance, what invariance truly is, and proposes a genuinely new foundation for physics.
A foundation where everything comes from one place.
Exactly. This foundation posits that light, mass, space-time, and gravity emerge from a singular invariant symmetry, the hypergravity coherence field. It envisions an entire universe generated from an absolute unbroken coherence. And our current incredibly successful physics is seen as a highly effective description of its emergent relational properties. The goal isn't to invalidate that success, but to provide a deeper, more unified understanding that potentially resolves long-standing contradictions and opens up entirely new frontiers for exploration.
And so we leave you with this thought-provoking question for you to consider. If what we perceive as fundamental constants and laws, things like the speed of light, the curvature of space-time, the force of gravity, if these are merely projections or reduction artifacts of a deeper, unbroken coherence, what does that really imply about the nature of reality itself and about our ability to truly observe it? What other shadows of invariance might we be mistaking for the source right now? And what revolutionary insights might be waiting for us when we finally learn how to look beyond those shadows and into the underlying light?
It's a compelling thought. By potentially understanding invariance as a property of coherence itself, not just of motion, space-time, or geometry, we might open up entirely new avenues for scientific discovery. It could lead to a much more unified and perhaps more elegant understanding of the universe around us.
Looking for the harmony, not just the notes.
Exactly. It encourages us to look for the deep underlying harmony, rather than just cataloging the individual notes. And perhaps, with this new kind of lens, the universe will reveal even more of its absolute unbroken symphony.